Okay, so we were talking about section 10.5 last time. We were talking about parametric surfaces. And the example we were looking at was actually this example, example 2, where you were asked to graph the surface of this vector function of 2 parameters. Okay, and we talked in the class about how by setting, like you notice there in example 2, it says which grid curves have u constant, which have v constant. So of course, if this vector function of 2 parameters u and v, if we set one of the parameters as a constant, then we have a vector function of just one parameter, one variable, and that generates a space curve. So for different, if we set the one parameter equal to different constants, it's going to generate similar space curves that when we put them together, we can get an idea of what the surface looks like. And in this particular example, if we set the v constant, we're going to get a helix. Okay, we're going to get a helix. And I don't know, and so like you see there in the figure 5, when the v takes on different constants, you see the v constant with the 2 arrows. That means when v is held to constant, and you have different, v takes on different values, the different constants, and then you let the u vary. The grid lines are helices. The grid lines follow helices, and if you put a bunch of helices together, you get a helicoid. Okay. Now, on the other hand, if you were to set the u constant and let the variable v vary, you would generate, it looks like ellipses. Okay, but it's much easier to set the v constant, and then observe that you get helices. So this is just kind of it's an example of these grid lines that they're talking about. I mean, you all see the grid lines in figure 5, right? But naturally, it will be helpful if we have MATLAB to help us graph this particular parametric surface. And so let's recall here here are the parametric equations for this parametric surface. Okay, and what we want to do is graph the parametric surface. So if we go into Blackboard, okay, let me see here, right, let me take this off. Okay. Okay, so who's seeing the Blackboard okay? Is the Blackboard coming up? All right for you all? Good, good. And there's some announcements here, but I'll talk about them later. Let me go into MATLAB programs. Okay, and then we click here to see the MATLAB programs. And section 10.5, parametric surfaces, there is a MATLAB program that corresponds to this second example from section 10.5. So if you click on the link for MATLAB program, it will download, well, you can download the M file and then click on it, and assuming MATLAB's installed on your computer, it ought to bring up the MATLAB. Okay, so let's see here. One moment. Let me bring up my my MATLAB for you. Okay, so there it is. There it is. This is figure 5 from example 2. And there we now use the sims command U and V because those are our parameters. And I type in the 3 parametric equations for X, Y, and Z. And then I use an easy surf command, as you see here. And in what I'm going to do is I'm going to well, maybe I can highlight it here. So you see here I have 0 to 4 pi. What do you think that stands for, 0 to 4 pi, 0 comma 4 pi? Why is that there? Domain. That's right, Yanu. It's the domain of what variable? Well, there's no t. There's no t. Our variables here are u and v. Those are our parameters. That's right. That's right, Ellie. U. That's the domain for u. It's gonna let you go from 0 to 4 pi. Okay. So since for signed function 0 to 2 pi gives you one period, one cycle. 0 to 4 pi, which should give us 2 cycles. Now, what about? And I appreciate all responses. Okay, we learn. Even when we respond and say the wrong answer, we still learn, right? Because you're going to get the right answer. Now, what about this? That's right, Hunu. What about this second 0 to 4 pi? What's that refer to? What domain does that go with? That's right, Charles. Right. That's right, Hanu. The V. Okay. All right. So let's go ahead here. I'm gonna, in the command line, I'm gonna do clear vars. Okay, just so I clear out any old variables. And then, as is my tradition, I copy the code and I paste it on the command line, and then I hit enter. And it should bring up, and try it yourself. Please try it yourself. And it should bring up a figure. One moment here. Let me get this off here. One moment. Hold on, everybody. I want to try it again here. Yeah, there we go. Okay, now let me bring the figure up. There we go. And if I go to tools, I can, let's see. I'm looking for, well, I can zoom out a little bit. I mean, there's different things, but maybe it's, okay, rotate 3D. That's what I wanted. So see there? And if you rotate it enough, you'll get it so that the axes are like what we have in the book. Let me see here. I'm just kind of playing around with it a little bit. Well, it isn't quite there. You see what I'm doing. You see what I'm doing. Let's see. I was hoping maybe I could get the axes to be like what we see in the book, but it just takes time. It just takes time to work through. But you get the general idea here. So how many of you graphed this? Okay, tried it and got this picture? It's definitely a helicoid, and it resembles the helicoid in the book. Are there any questions? Who did it successfully? Who opened up that MATLAB program and got this parametric surface? I'd like to at least feel like a few of you. Okay, worked for Charles. Good. Hold on here. And it worked for, sorry, I got so many windows open. Too many of them. Hold on, where am I? All right, hold on, let me stop the sharing. Where'd it go? Okay, hold on. All right, Ellie as well. Okay, great. So there you go. And I'll point something else out too. Good, you knew. That's excellent. So, it's always good to participate. Always good to participate. Let me see here. One moment. So you'll notice also here in the MATLAB code, you'll notice in the top right of the script editor, it's yellow. So yellow means that it should run, but it's going to point a few things out. So like, for instance, if I see the little line there and hover over it, it says easy surf is not recommended. You can use fsurf instead. Well, there are different commands. MATLAB gets updated every year, and I have the commands that I like to use, just because sometimes. Well, I mean, I'm comfortable with these commands. They work. Easy surf, that means, hey, it's easy to graph this parametric surface. It's a quick command. It seems to make. I like the wording. But, if you want to use fsurf, that's fine. Okay, any questions before we move on? Okay, well then let's go ahead back to the book here. Back to the book. So they talk about some other examples too, like for instance, parametric equations for a plane. Okay, now a plane, well, you can write a plane as a function of x and y. So, but we can also we can adapt the code that you just saw there in MATLAB to graph a plane using, because any surface can be represented as a parametric surface. Okay, parametric surfaces are more general than like having a function of x and y. Parametric surfaces are good for all the surfaces you're going to encounter. So how would we do parametric equations for a plane? Well, look at figure 6 here. And what they do is they have a plane. And in the plane, they have two vectors, A and B, in the plane. And if you take, well, let me actually, hold on, let me bring this up just a little bit. One moment. Yeah, I want both to be in here. All right, so you see above there, figure 6, it gives the, one moment here. It gives the vector function of two parameters u and v, and it writes it as r sub 0, the vector r sub 0, plus the vector u times the vector a plus r sub 0 plus the variable, the parameter u times the vector a plus the parameter v times the vector b. And that is that vector function of u and v will trace out a plane. It will trace out a plane. So here's what they're doing. Maybe I can give you a little guidance on this, a little more guidance. If in the whiteboard here, Okay, so let me just you know, here's a plane, okay, and here's the origin, okay. Well, we could draw a vector. I want to say this the right way. We could draw a vector r sub 0 to a point p sub 0 in the plane. What we could do, though, then, is from that point p sub 0 in the plane, we could have vectors u and vector v. See that? Vector u and v. Okay, I'm taking my volume up a little bit. Okay. And if I were to, like, let's say I wanted to hold on here. Let's say I wanted this point right here on the plane. Well, what we could do, or better yet, maybe this point here. Let's pick that point. So what I can do is, hold on here. Yes, I can have this vector here, and I can have, be a little careful here, this vector here, and this vector, hold on here, actually hold on one moment. I want to call this vector A and this vector B, okay? So the purple vectors, this purple vector is vector A, and this purple vector here is vector B, okay? One moment. All right. Now, the green vector here, and I'm sorry, I want to be consistent with the book, class. I want to be consistent with the book. I should have looked a little more carefully at the picture. I mean, everything, the picture's good, but I want to be consistent with figure 6 in the book. So I got to slow down a little bit here. I'm going to call this vector B. Okay, this vector here. And I'm going to call this vector A. This vector here. Okay. Now, this green vector here is equal to some variable u times the vector A, and this green vector here, okay, is going to equal some variable v times the vector b. Well, if I were to draw this vector here, what's that vector equal to? What would that vector be? Good, that's right, Ian. Good. This vector would be u times a, u times a vector a plus v times a vector b. So this means then, that if I want to identify from the origin a point on the plane, then that blue vector there, which goes from the origin to a point on the plane, would be what? That's the sum of two vectors. What are the two vectors? That's right. Good, Ellie. R sub 0 plus u times a plus v times b. And so this is why, I mean, well, I mean, hold on. Okay, so for a plane, in three-dimensional space, the vector function of two parameters, which is r of uv, that's going to equal the some vector r sub 0 that goes from the origin and touches a point on the plane, plus the vector ua plus vb. Okay, are there any questions on that? Who's feeling okay with that? Who's feeling good with that? Maybe give me a thumbs up if you're, all right, Hyunwoo's good. And Ian and Ellie, excellent. And Gordon and Kino, wonderful, wonderful. Thank you, everybody. So now, when I go back to the book, okay, when I go back to the book, okay, then now this should make good sense. And of course, that vector function of parameters u and v is the vector function for a plane. Only a plane now. That's not a vector function for another parametric surface. It's for a plane, but it'll handle any plane. And if we wanted to then write out the parametric equations, okay, if we were to write the vector r sub 0, a and b that way with those components, then these would be your parametric equations. Okay, are there any questions on that? Okay, well, let's go ahead and look at another example from the book, and then we'll look at a few of our own here. Parametrizing a sphere. Here's a sphere with what's the radius of this sphere? Radius A. Good, Keanu. Good, Ian. Well, we could use to I want to say this the right way. Hold on. Let me just remove some of the highlights here. We could use spherical coordinates, because spherical coordinate, well, the A is a constant, okay? But if the A is set constant, then with spherical coordinates, you have the other parameters, angles, theta, and phi. So, I mean, X is defined as A. I mean, you're used to X being equal to rho times sine phi times cosine theta. But our rho is equal, that's the radius of the sphere. That rho is equal to A. So X equals A times sine phi times cosine theta. Y equals A times sine phi times sine theta. And Z equals A times cosine phi. So those parametric equations will then be trace out a sphere of radius A. Okay, and let me just highlight this. Hold on. Yep, and make this big. So this here, the vector equation for a sphere is given there. If you let phi and theta vary, well, theta is going to vary what? What can theta go between? What angles can theta? 0 to 2 pi. That's right. And what angles can phi go between? 0 to pi. And so if you I mean, think of this vector equation, R of phi and theta. Think of like having a pencil, and the pencil is going to obey the vector equation, and it's going to trace out whatever the domain is for your parameters. Okay, if you did that for this particular vector equation, you would trace out this sphere here. Okay. We would trace out a sphere. And actually, what they do in the picture here, they're always talking about these grid lines. In figure 7, let me see if I can move that up just a little bit here. Figure 7, you have the horizontal axis is phi. In the first picture there with the rectangle, the horizontal axis is phi, and the vertical axis is theta. Maybe I'll actually make it show full way here. So that's your domain. That's your domain for this vector equation, because I mean, notice phi on the horizontal axis is phi in figure 7, the first picture there. Phi is allowed to go from 0 to pi, and then the vertical axis, theta, is allowed to go from 0 to 2 pi. And so the domain of your, I mean, if you think about your parameters as coordinates, theta and phi, or I should say phi and theta, the domain is going to look like this rectangle. And what you can do, you see, is you see there like how, for instance, they set well, You see there how they set phi equal to c? You see that red line segment where they let phi equal to c? Okay, well, all right, well, if phi is equal to c, then in terms of the sphere below, the grid line on the sphere would be that circle. See that circle on the sphere that says phi equals c? That's your grid line. Now, please let me know if this is uncomfortable for you. If you have any questions, odds are if you have a question, there might be a few other people that have the same question. In this sphere below, the grid line phi equals c, which is that like circle. It remember phi is measured from the positive c-axis. So it's like what they're doing. I'll show you here. That's correct, Ellie. That's exactly right. If you take like your z-axis here, okay, and like this is the origin here, and you go down some angle, like let's do something concrete. Like let's say, let me just see here. Yeah, what's I want to say this the right way. What's good, Hunu? What's phi equal to here for cheating a little bit, but well, I wanted something a little easier. I was going to say pi over 4. I'm sorry if it's not perfectly pi over 4, but I think you know. So if phi here is pi over 4, and we were to let theta vary, okay, what would happen is if theta varied, you trace out, and I'm sorry I can't get it perfect. You would trace out a circle. In other words, this circle here is phi equals pi over 4, because any point on the circle, okay, like let me ask you this, what would this point be over here? What would that, well, I want to be a little careful here. I want to be a little bit careful. But if I were to define theta and phi here, we know phi is pi over 4. Okay. So I'm not talking this point. I'm talking this point way over here. Phi is pi over 4. What's theta equal to? Pi. That's right. See that? What about this point here? I'll put a point in black here. Okay, that black point has a theta and a phi. Phi is pi over 4. What's theta going to equal? Well, almost, you're almost there. Well, would it be pi over 2, or would it be 3 pi over 2? Which is the right answer for this point here? So you start here to measure theta. You got to, oh, I see what you're saying. Oh man, hold on. Oh man, yeah. I guess it would be 0, right? If the x-axis is coming out like directly at us, I guess it would be 0. Didn't even think about that. I'm so used to the x-axis, being to the right. But you see what I'm trying to say? You see what I'm trying to say? All the points on this grid line, here are theta is going to vary, but phi is always equal to pi over 4. Okay, does that make sense? Okay, good. Well, then let me go back here. Wait, hold on. Theta goes for spherical coordinates, theta goes from 0 to 2 pi. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. So now in figure 7, if you notice where they have theta equals k, the green horizontal line there, okay, theta equals k. Well, in terms of the picture, the grid line on the sphere, that's the theta equals k grid line. So there you're letting phi vary from 0 to pi, but theta is always held constant. And what in that sphere there, what does theta look to be about equal to? So they say theta equals k. Okay, but in the picture, pi over 4 is the right answer. Because remember, it's 45 degrees from the x-axis. So I mean, okay, it's an estimate, but it looks to me to be about pi over 4. Let's see, does theta equals k? Theta equals k makes a full circle. Oh wait, hold on now, hold on, let me see. Let me see, that's a good question, wait, hold that thought now. Let me see here. No, now wait a minute here. Oh man, you're right, Ellie. Ellie's right. I was incorrect on that. Thank you, Ellie. Since phi goes from 0 to pi, the grid line for corresponding to theta equals k is only like it's only a half circle. It's not a full circle. That's right. Because phi goes from 0 degrees, measured from the positive z-axis. Phi ranges from 0 degrees to 180 degrees. So that's right. It's just a half circle. It's just a half circle there. Thank you. Thank you. Okay, are there any questions on that? Okay, so it's really important to be comfortable with this concept. Okay, it's really important because it's gonna come up. It's gonna come up a lot. This idea where if you have it's sort of the general idea here that if you have a domain in the UV plane, which is the parameters are U and V, if you draw your vector function along those vertical and constant line segments there, where you're holding one of the parameters constant, it traces out space curves on the surface, C1 and C2. So it's a very common theme, and it's important that you're comfortable with it. And with the sphere that we just looked at, that was a concrete example of that. And also the helicoid that we looked at in example 2, another concrete example. So if there are no questions, let me go ahead here and let's go ahead and look at another example here. Let me give you a moment to copy this example down. Okay, so in this problem, what we want to do is we want to find the parametric representation for the surface described by the part of this sphere. What's the radius of this sphere, by the way? 10, that's right. So we want to find a parametric representation for the surface described by this part of the sphere that lies above the cone. So now again, the cone, back in section 9.6, you have a table 2, and you're going to need to, it'll be helpful to refer to that sometimes for the section 10.5 exercises. Many of them are multiple choice, so you have to be careful before you answer. But like x squared plus y squared equals z squared is an equation of a cylinder, because, you know, underneath you have like a 1, 1, 1. You have constants underneath. Okay, and I'm actually looking at section 9.6, and, you know, I can like have 1 squared, 1 squared, 1 squared. So A equals B equals C. They're all equal to 1. They don't all have to be equal for a cone, but I'm just saying in this case, those are my values of A, B, C. So that's going to generate a cone, right? And the cone, the standard cone, I mean the general form of the cone, you have the origin here in the middle, and then the cone goes above and below. For this cone here, is it this entire cone? We were able to take this equation and express it. We squared both sides and got this, but we really do have to work with this equation. Okay, so we recognize it as part of the cone family, but is it this whole cone here? Is it the entire cone? Is that what we have here? Just the top half. Good. Why? Why, Hanu, is it just the top half? That's right. We have a positive radical here. So if we were to take the equation of the general cone and we would square both sides, right? We would get plus or minus square root of x squared plus y squared, right? That's one of the things you were taught to be careful about, right? When you square a variable, you have a plus or minus. But here, we only have a plus square root of x squared plus y squared. So it's just going to be the top half of the cone. There's the origin there. Okay, are there any questions on that? Well, the radius, the cone, we don't normally talk about a radius for a cone. We don't have a cylinder here. We have a sphere and we have a cone. We have a sphere here. Okay, x squared plus y squared plus z squared equals 100 is the sphere. Hunu, for x squared plus y squared equals z squared, that's a cone, and we don't normally talk about, I got to be careful how I phrase it. We normally refer to radiuses or radii when we have cylinders and spheres. Now a cone, I just want to be careful what I say, but this is not like a cylinder at all. It's a cone, and I want to say this the right way. Yeah, don't worry about that now. Okay, let's keep it simple. Let's keep it simple for now. Let's keep it simple. Okay, all right. So, hey, what's the first thing we might want to do? Excellent. What's the first thing we might want to do in this problem to help us? Would it be nice to see the surface, to get an idea of what the surface looks like? Yeah, it would be nice. So, well, and Ellie, you're right. Let's look at a picture here. Here's a picture. Here's a picture. So what I'm doing is that's right, Charles, an ice cream cone. Okay. Okay. So here's the cone. Here's the cone. Positive top half of the cone, but it gets stopped on top by the sphere. The cone bumps into the sphere. Okay, and the intersection, of course, of the cone and the sphere would look like what? What would the intersection of the cone and sphere be? What shape, what figure would it be? What shape would it be? It would be a circle. Absolutely right. Good, good. So the surface that we're talking about is what is shaded here, because that surface, you see the penciled shading here. Okay, that penciled shading, that is going to be the part of the sphere that lies above the cone. I mean, the sphere, right? The sphere keeps going, right? But we're not interested in the rest of the sphere. We're interested in the part that lies above the cone. So in order to figure out parametric equations or a parametric representation for this surface here, which looks like, well, it's like think of an ice cream cone. The surface is like, think of a bowl of ice cream. The surface is I don't know, you lick the ice cream, you lick the ice cream, it's like the outside of the ice cream. You know what I mean. So we have to find the parametric representation. Well, one thing that's very important is to figure out where these two surfaces intersect. So I set the two surfaces equal to each other. Okay, I set the two surfaces equal to each other because I want to solve, I want to get an idea of what, what I'm going to do here is I'm going to assume here that my parameters, that's right, I'm going to assume my parameters are x and y. Okay, and I need to know what's the domain on x and y. What's the domain on my parameters? Well, clearly, any point on my surface, the xy coordinates are going to have to, the xy coordinates are going to have to fall inside this circle here. Right? If I were to project that circle down into the xy plane, okay, and look at xy coordinates. Of course, the z coordinate 0, but let's focus on xy. All the points, all the blue points on the surface, their xy coordinates are going to have to fall inside this circle here. They're going to have to fall inside that circle. So what I'm trying to do is find out the equation of that circle. And so I set the surfaces equal to each other, and when I solve, I get x squared plus y squared equals 50. X and y values that satisfy this equation are going to be coordinates. They're going to be coordinates of the points, okay, the points that lie on the intersection of the cone and the sphere. Okay. So therefore, my parametric representation is given here at the bottom. I let x be x, I let y be y, and then z is the square root of 100 minus x squared minus y squared. This is my z. Now, why is that my z? Why does z have to be square root of 100x squared? No, why does z have to be equal to the square root of 100 minus x squared minus y squared? Why is that? Because it's the top of the sphere. Good, Ian. Good, Ian. I mean, in terms of graphics, that's why. It's the top of the sphere. The sphere the points on that surface, that shaded surface, X, Y, and Z. I mean, every point on this surface here, every point has an X, Y, and Z coordinate. Well, we know that X squared plus Y squared is constrained to be less than or equal to 50. So in terms of X and Y, any point that is going to be on that shaded sphere, their XY coordinates have to obey this constraint. But the Z coordinate has to obey this constraint. Z equals square root of 100 minus 6 squared minus Y squared. It's like in this case, you're letting X and Y be free, but then the third variable is constrained. Okay, is that all right? Are there any questions on that? So in WebAssign, this would be below, this would be your answer. And normally what WebAssign does is they might help you out a little bit. They might, like in the answer, have an X there and a Y there, and then you have to figure out what this is, and you have to, what that Z is, and then you have to figure out the constraint. Okay, so this is where you have parameters X and Y. Are there any questions on this? You have to let me know. Who's feeling okay so far? Maybe give me a thumbs up. Okay, very good, Ian. Very good, Ellie. Very good, Charles. Okay, very good, Juliana. Excellent. Okay, Hunu. Good, good. Now, there was a sphere involved in this problem. So here our parameters were X and Y. But what if I wanted to do this problem with parameters theta and phi? Okay, what if I wanted to use different parameters? What would the vector function be? Well, let me show you on the next page. Let me show you what I call the second approach. May I go to the next page? Okay, let's go to the next page and take a look what I have here. One moment. Okay, so first of all, why? So this is my vector function of theta and phi. Why do I have a 10 here? Why do I have a 10? That's my radius. Okay, and we know how X, Y, and Z are defined, and that's from the sphere equation. And our surface is on the sphere, so X equals 10. Okay, and then the parametric equations come from the definition of spherical coordinates, but we have to have a constraint here. Now theta will go from 0 to 2 pi, but phi is constrained to be from 0 to pi over 4. So you see, along with the vector equation of the two parameters, you also need to include what the domain is on those parameters. So theta going from 0 to 2 pi makes sense because that'll create like the circles. And that, I mean that'll I want to be careful how I say this. I didn't mean to say that. It's these two parameters together that will generate the surface. But why does phi stop at pi over 4? Well, again, we're going to do the same thing we did previously. We're going to set the two surfaces equal to each other. Okay, so well, now hold on. No, we're not going to do that. No, what we're going to do is we're going to look at the cone. We're going to look at the cone. Okay, so the cone, the boundary. Okay, the boundary between the sphere and the cone can be defined by the cone, certainly. Well, what's the equation of the cone? What I do is I substitute in the spherical coordinates for z and x. And then I solve this. I solve this equation here. Okay. Because I'm trying to figure out, I mean, the points on the intersection of the sphere and the cone have to obey the cone. Okay, so the point, what would phi be for those points that are on this intersection here? And if you do the math, it turns out that phi will equal pi over 4. So phi between 0 and pi over 4 will give the desired points. And there's a nice little picture there on the right. And, you know, Dr. Duty's stuff here. Put that on there. Okay. Let me give you a moment to copy and look at the diagram, and I just want to see if you have any questions. And do you see here how phi would range between 0 and pi over 4, between 0 degrees and 45 degrees. And then, of course, you just, you know, I drew just a couple of, just a little bit of information there for you. So all the points here, phi has to be between 0 and pi over 4. Same over here. All the points here phi has to be between 0 and pi over 4. Now, theta changes, right? It has to change in order to get the points over here. Incidentally, for these points here, in this part, all these points here, what would theta be between? For this shaded area, for this part of the surface, this half here. Phi equals pi over 4 there. Phi's constant at pi, well, no, I'm sorry. Phi goes between 0 and pi over 4. Okay, yes, it does. But what would theta be between, just for this half of the surface? And pretend that the x-axis is coming out at you, directly at you. Pi to 2 pi. That's good. That's right. Pi to 2 pi. Good, Ellie. Good. So I think you're getting, hopefully you're getting a feel. How many are finding this pretty helpful, this example? Decently helpful. All right, Gordon, I like that. I wanted to do kind of a tough one with you. And they have, other examples in the book, but I wanted to do a tough one. And to show you, parameterizations, you can have different parametric representations of a surface. In this case, the first parametric representation was with parameters x and y. This representation, this parametric representation, is with parameters phi and theta. And so, you can even, like in WebAssign, like when you do a problem and it wants like information regarding like what the domain is for the parameters, you could take your parametric surface and use that MATLAB program from section 10.5 under the MATLAB programs that I showed you. You could take that MATLAB program and adapt it to the exercise you're doing, and put in the domain on the domains, the domain for your parameters, and and see if it makes sense, right? How many might try that on maybe homework or the next exam? Just to kind of check your answers. Sure. Ian says probably, Ellie says probably, Kino. And this is another reason why I like to give 3 hours, so you can do stuff like this. And I like to break the exam up into parts because it allows you to do kind of things like that. Good. Kino, Ellie, and Ian would maybe try that. Are there any questions before I stop Malik would too. Excellent. Are there any questions before I stop the recording here? Okay, I'll stop the recording.